In 7.3c, we're going to explain how the shape of the sampling distribution is related to the shape of the population distribution. In the previous notes, our population was actually normal, therefore our sampling distribution was normal. But what if the population is non-normal? We have to use this thing called the central limit theorem, and I want to show you how it works. Here we have in front of us a population that is skewed to the right. Now what they've done is they have taken a sample size here of 5, and then 10, and then 16, and they ran each of these, it looks like, 10,000 times. So sample size of 5, compute the mean, plot it, do it 10,000 times. You're going to notice this first one of a small sample size of 5 actually looks approximately normal. The sample size of 10 does too, and so does the sample size of 16. So what we can actually conclude is this, that it looks less like the population when we take our sampling distributions and more like a normal distribution. And from this we can make some conclusions. Now going forward, if we have a population that is not stated as normal, you are going to have to clarify your normalcy by talking about the central limit theorem. And here's what the central limit theorem says. It says here that if you draw an SRS of size n from any population whatsoever that has a mean of mu and a finite standard deviation, means there's an answer for it. When n is large, the sampling distribution of the sample means, or of x bar, is actually close to the normal distribution. It's going to look like this normal distribution here, with the mean of mu and the standard deviation of sigma over the square root of n, which is what we calculated before. Well, how large a sample size should we go? Well, how large a sample size is needed to be close to a normal depends on the population distribution. More observations are required if the shape of the population distribution is far from normal. The central limit theorem, or what we call the CLT, tells us if we have n is greater than or equal to 30, then we can say our sampling distribution will be approximately normal. Let me show you with even a more odd population. Here we have a very weird looking population. It's not skewed right or skewed left, it's just distributed very oddly. What they're going to do in here is take 10,000 samples of various sizes. Here they took size 2, size 5, and then size 25. Notice for this, because it's such a bizarre population, when a sample of 2, it still looks bizarre. This is definitely not considered approximately normal. So they went to size 5. It's still not approximately normal. But as they approach 25 or as they approach 30, you're going to notice it starts to look approximately normal. Therefore, this is where the central limit theorem is really coming from. If our population was slightly skewed right or left, you really don't need to get up to 30, but that's the rule that we use. If our population is really weird and different, we absolutely need to go up to 30. So going forward, if it is not stated that the population is normal, you now have to state the central limit theorem and show that the sample size is greater than or equal to 30 in order to say approximately normal for your sampling distribution and to compute probabilities.